Hello everyone, my name is Ayon and I'm working with Tom Cleland at Cornell University. Now today I'm going to talk about a machine olfaction algorithm inspired from the mammalian olfactory bulb, but not the entire algorithm, some of the key features. Now let's imagine a situation where a fox is looking for a prey. The situation can be very different. The order of interest can be strong and there will be low background interference. And you can have multimodal inputs, like in this situation. It can be visual plus odor. Or you can be in a situation where the order of interest is weak, and you have high background interference. Now, I want an algorithm which does this. And we call this situation learning in the wild, and this is the olfactory heart problem. Now, I want to design a single algorithm which can do this. So what can be the challenges? Now, I'm not saying this is exhaustive list. If you care about general AI, it is much more bigger. Now, the environment can be variable. You can have odors at unpredictable concentrations. Odors always have overlapping receptor activity, temperatures, humidity. And incoming data may have missing values because sensors are always noisy and sensors go bad. And if you're caring about application in autonomous systems, you cannot always afford to have train sets labeled. And sensor drift, which is unavoidable. Now, if you want to talk about the algorithm, it must exhibit concentration tolerance. The algorithm must be able to recognize odors at novel concentrations, but sometimes you also need an estimate of concentration. It must be able to identify the signatures of known odors despite substantial interference. And we want rapid and learning from few shots. And this is very important. It must support online learning and no catastrophic forgetting, and I don't want to store data. Once it has been trained, I want to get rid of that data. Now, I said labeling train set is hard, so it should support unsupervised learning or at least semi-supervised. And I'm talking about learning in the wild, which means you cannot afford to have odors which you have been only trained with. So you should have a none of the above option and a classifier confidence. And you need to have a solution for sensor drift. And it must be robust to wild poorly behaved inputs without parameter retuning. And most of my talk today is about this last point and some others. And in fact, the algorithm that I'm going to talk about cares for all of these things. Now, we have been testing our algorithm on many data sets, olfaction and some other data. But today I'm going to talk about only results from this data set because I don't have a lot of time. Now, this is the UCS, the gas sensor data set. It has 6 odors at different concentrations: ammonia, acetaldehyde, acetone, ethylene, ethanol, and toluene. There are 1,300 samples, but the data was taken about 3 years, and hence there is sensor drift. And because of that, the sensor responses change across time. So it has been split into batches. Now, this batch is different from batch learning and deep learning. So don't mix up that. Now, here, batch 1 comprised of recordings from first 2 months, and batch 7 comprised of recordings from 21st month, and batch 36 comprised of recordings from the last month, and that was done after the sensors were actually allowed to contaminate. Now, the algorithm is inspired from the mammalian olfactory bulb. It's an attractor network, and it's a multi-layer network, but each of the layers have different computations towards different goals. It's a spiking network. The architecture is part of the algorithm. It uses local synaptic rules. So you should expect less model compression efforts. And in fact, we do have a version of this model on Lohi. Now, the data sampling is inspired from the olfactory epithelium. The preprocessors, my main focus, is inspired from the glomerular layer. And then you have the principal neurons projecting to the inhibitor feedback neurons. Now, the core learning network is comprised of this principal neurons, mitral cells, projecting to the inhibitor feedback interneurons, which are the granule cells. Popularly, this layer is known as external plexiform layer. Now, from now onwards, keep in mind, when I say mitral cells, I mean these principal neurons. And when I say inhibitor feedback interneurons, I mean granule cells. Now, very briefly, so you have the sensory input. And in the mitral cells, this sensory input is going to be converted into a spike precedence code. Stronger sensor input, the mitral cells are going to fire earlier. Weaker sensor input, the mitral cells are going to fire later, or no spike at all. And all this in a single gamma cycle. And the granule cells are going to learn those input feature combinations, and it's going to deploy as feedback inhibition to the mitral cells. And the role of this inhibition is that you want to shape the mitral cell spike timing patterns, thereby creating an attractor-like network. But I'm not going to talk about this attractor network today. Some of you might have seen the attractor network results. What I'm going to talk about is these mitral cells projection to these granule cells, and the learning is based on asymmetric STDP, and that's because I also want to talk about preprocessors. Now, like all networks, for optimal performance, the core learning network requires that the sensor input adheres to some ranges of amplitude and statistical structure. Now, I am talking about learning in the while, which means I have no control over the input that is coming in. But I want the network to learn and respond productively to any input source. And for that, for simplicity, our result for classification was the assessment of interneuron activation patterns. And we can do that using multiple ways. We can use Hamming distance, or you can use overlap, and there are other techniques too. Now, so the first thing I'm going to talk about are the preprocessors. These are not very complex things, but these are very important. As I said, if you have inputs from arbitrary set of sensors in natural environments, it can be diverse and unpredictable. Now, this figure here, the x-axis indicates these 16 sensors, and the y-axis indicates the sensor responses for 3 different odor types. And these odor types are very widely different. And here the x-axis indicates the odor sample indices, and the y-axis indicates the fraction of interneurons, the granule cells, that spike for each of these odor. Now, if you see, they're widely different. And for one of the case, it is 0, and we don't want that. In an attractor network, for all of these odors, you want at least some of them in the interneurons to spike. Now, you can definitely say, just retune the network. That's very easy. But parameter tuning is very costly. We want to avoid that. These parameters are tuned. In fact, I did that using some synthetic data sets, and they are tuned towards a particular goal. And we don't want to change that. We might gain some accuracy on some simple data sets, something, but that also means that you are overfitting. So I don't want to touch the parameters. I want to modify, do something on the data. This is something I say here. So the solution is to apply signal conditioning so that the network will just work on arbitrary data sets without parameter retuning. And then you can potentially use the same parameters, same network, for different data sets. And in fact, we have done that. Now, we also have a metric for determining the goodness of the signal conditioning or goodness of preprocessing. It's very simple. So you have two panels. V is the vector of internal spike counts across different odor samples. So here it will be a 3-dimensional vector. And you have two penalties. One is the no spike penalty, and the other is the interneuron spike count similarity. So we want the interneurons to spike. And the no spike penalty ensures that it spikes for all the odor samples. The other is interneuron spike count similarity. It ensures that for all the different odor types, the interneuron spike counts are approximately similar. Now, on this figure, on this x-axis indicate the sensor indices, and the y-axis indicate the sensor responses. These are the raw sensor responses for 6 gas types at 4 different concentrations. And you see that the mean sensor responses are widely different. And on this figure, the x-axis indicate the 24 samples, 604, and the y-axis indicate the fraction of interneurons for that spike for each of these. And you see that they are widely different, but that's not the only case. For some of this, they are 0, and we don't want that. And hence, the no spike penalty is 0, and goodness of preprocessing is 0 here. Now, this is the same figure as the previous one, but I've sorted the sensor responses by amplitude. You're going to realize the importance of this step after a few slides. So the first thing, it's very simple. It's the uniform sensor scaling thing, but I determine the maximum sensor responses from 10% validation set, and use that to scale both train set and test set and all the subsequent data. And that doesn't mean, so we don't have a strict requirement of the values to be 0 and 1. It can go beyond 1 to some extent. Now, it is useful because this step facilitates the use of highly heterogeneous sensors or data sets. And our algorithm is based on combinatorial coding, so we need this sensor scaling. And if you look at this sensor responses here, for each of the gas types, which are a particular color, the sensor responses are like different, and they indicate odors at different concentrations. There are 4 red ones. And the fraction of interneurons that spike are still widely different, and for some them it is still 0. Hence, no spike penalty is 0, and goodness of preprocessing is also 0. Next thing we should do is non-uniform sensor scaling. It is useful if the training set is small. So we modulate the sensor scaling by an equidimensional vector drawn from a uniform distribution. And this is, again, inspired from biology because heterogeneity is abound in biology. But still, if you look at the fraction of interneurons that spike, they're widely different, and for some of them it is 0. So we should not stop here. Next is the concentration tolerance. It is inspired from the mammalian olfactory bulb, glomerular layer. So here, an intercolumnar network, which is the periglomerular cells, integrate the net input across columns and deliver it as graded shunting inhibition to all the columns, that is the mitral cell columns. And if you look at the sensor responses for each of the gas types at different concentrations, the sensor responses are kind of similar. They're bundled together. And that is helpful because you don't need to train the algorithm with all the possible concentrations in nature. So that is going to help you in few-shot learning, and we see that. And if you look at the fraction of interneurons that spike, they are widely different, but they are non-zero. And that's because the area under the curve, I mean, forget about the individual sensor responses. If you think of it as a curve, the area under the curve are approximately constant for each of these sensor responses. And here, the good days of preprocessing is a bit better, but not the best. It is 0.56. Now, the last step is heterogeneous duplication. And if you look at the sensor response profiles for all the gas types after this step, they are approximately similar. And if you look at the fraction of interneurons that spike, they are approximately similar. And the GP is 28% improvement, which is 0.884. Now, what we did here, it is again inspired from biology. Each of the sensors in the olfactory bulb, which can be the receptors, they project to multiple ET cells. So we took 5 of them. It can be different. And these ET cells randomly project to multiple mitral cells. We call it system mitral cells with heterogeneous weights. And there is no learning here. And I'm not talking about random projection to low dimensions. Now, but I'm projecting it to high dimensions. So I have these 16 sensors. I projected it to an 80 dimensions. And if you do that, you see that the sensor response profiles are kind of similar across different sensors. But if you remember, these are sorted sensor responses. So if you look at the individual sensor responses here, for each of the sensors, you see that the gas type for a particular different gas type, the sensor responses are different. In fact, after doing all this, we don't lose any accuracy. We still retain accuracy, but we don't have to retune the network for all the sensors. So this is all about the pre-processing step. So this is what I talk about to you now. Now I'm going to talk about these principal neurons, mitral cells, projecting to the granule cells, again using this batch drift data set. Now I'm talking about learning in the wild. So it must be able to deal with online learning. It shouldn't suffer from catastrophic forgetting, which means I have to modify the data set a bit. So each of these batches had 6 or 5 gas types. So we split each of the batches into groups. So group 1 had ammonia. And the task was, after I trained with ammonia, with one of few shots, your task was to either detect ammonia or say none of the above from the entire gas. So you have 6 gas classes, and you have to see either ammonia or none of the above. Then I'm going to train the network with acetaldehyde. And you're supposed to remember ammonia. You cannot forget ammonia. And your task is to predict ammonia, acetaldehyde, or say none of the above from all these 6 types. And then you can do it many times, depending upon how many you have. Now, you can always Campbell this order. This is not the only order. So you can do both incremental learning and incremental class learning. So I did that, and but I wanted to test the capacity of this setup, like whether this setup is appropriate for online learning. So I trained a simple multilayer perceptor with ammonia and acetaldehyde, and you see that it remembers what it has been trained recently. But later on, if you train with acetone, ethylene, the performance drops. It suffers from catastrophic forgetting. And there's nothing new about it. We know this. Now, I trained this EPLFA, which is this feedforward algorithm, with ammonia, and you saw that performance is high, and then acetaldehyde, it doesn't drop, it is still high, and acetone, ethylene. So you see that in our EPLFA, which is the algorithm that I'm talking about, it doesn't suffer from catastrophic forgetting. Now, again, there's another challenge in machine olfaction, that is the problem of sensor drift. So on the left, you see the sensor responses of 6 gas types. And they are widely different, and I showed you this graph before. And on the right, you see the sensor responses. In fact, the same sensors are there of the same gas types after 20 months, and they have degraded. And this is bad. Sensor drift renders this prior learning obsolete. But I talked about this pre-processing. So if you apply these pre-processing steps, you can recover the degraded signal from the sensors. So if you compare the sensor responses on the left and right, they're kind of similar. But that doesn't solve the entire problem. We still need to retain the network. So the solution for sensor drift is that you use it, test it. As soon as there is a failure, just retain the network. But the advantage of using this EPFL is that the learning is rapid. You don't require a lot of training. It's few shot, And you don't have to worry about when you're going to lower down your learning rate and all those things. Also, it doesn't require any hyperparameter U-tuning. In fact, you can use the same set of parameters, and preprocessing are going to help here. And you don't need to wait for the entire train set ability. It's online learning algorithm, so you can update the model later. And you get a classifier confidence and none of the above options. So you know exactly when you need to determine when you need to reset the network. So we did that on this entire batch drift data set. The x-axis indicate all the batches, and y-axis indicate the accuracy. And you saw that we get good accuracy, and also it improves with more shots, even for the later degraded sensor batches. Now, I don't have it here, but actually we perform better than all the other available published work on this data set, using less train examples and also with less features. So I presented a learning algorithm, spiking neural network based, spike timing based. There's no rate coding here, which learns rapidly, few shot, and online learning, and robust classification under noise. And we presented a series of signal conditioning preprocessors, some trivial, some novel, but powerful, that enable this algorithm to usefully process poorly behaved data sets without hyperparameter tuning. And this is helpful when you have signals with dissimilar sensor statistical distributions, signals presented across ranges of concentrations, or you have signals from low intensity or degraded sensors. Now, heterogeneity is abound in biology. And we saw that non-uniform sensor scaling preprocessor helps, and heterogeneous duplication of input streams in the preprocessor network helps statistical regulation. We saw that in the last step. And I didn't talk about this explicitly, but when you have heterogeneity in the spiking thresholds of neurons, your algorithm's performance is improved. And we provide a solution for sensor drift where you can rapidly retain a network when the sensor response is degraded using very few shots, and you don't require hyperparameter U-tuning, or you can do it in online fashion. That's it. So I want to thank my advisor, Tom Cleland, my committee members, Al Molnar, Thorsten, Joachim, David Phil, and David Smith, Nabil at Intel, my lab mates, Christian Linster, all the funding agencies, and definitely Cornell. Thank you.
Thank you very much, Ayon. We have a few minutes for questions. So, do I hear any questions from the audience? There's one over here. I've got the microphone.
Thank you. Have you demonstrated the efficiency of the algorithms for different classes of gas sensing, or gas sensors, I mean, on different sensors?
So this is this result is from MOS sensors, yes, but we're also testing it on polymer sensors. And the other, actually, I didn't say it, but we're also testing an algorithm on other biomedical sensors outside olfaction.
Can you have this input tab?
So Paul Rhodes gave a presentation, I don't know, 4 or 5 years ago on DARPA-funded work doing a similar sort of thing. I'm curious if you can compare the work that they did was evolved machines.
So I've never attended Paul's work. So I saw one of his videos. The thing is that I don't want to make any comments right now because, see, I have to know his exact work. The thing is that it's hard for me. The thing is that I'm looking at the biology, and I'm also looking at the machine learning side, and I'm trying to test it on real-world algorithms. So unless I don't see any good performance on real-world data sets, I'm not going to trust anything. And that's because I'm an engineer. Because I want to see, I don't want to improve anything from biology unless I see that it is useful.
Okay, is that a hand?
Your finger. Sorry. Yeah. So you have this basically this like heterogeneous projection. You use this kind of thing as a regularizer, right?
Don't think of regularizer in machine learning form, like lambda or something.
Okay.
Don't think of that.
So how do I think of it?
Well, it's more like modify that data, like project to high dimensions, so that you don't have to return the parameters. So the mathematical part is like we are still in the process. We're not formulating it right now because I won't suggest you to think of it as a regularizer. I mean, that's definitely not the same thing because.
Okay. Okay, then. Well, yeah, I don't really know what that means. Then.
Yeah. So.
Okay, any further questions? If not, then we'll thank Ayon very much again.